this is going to be the last topic. So this is just a small topic that I wanted to discuss. It is called invariant subspaces. So in this video, we'll see what are invariant subspaces, and we will see some of the examples. And at the end of the after this invariant subspaces, I'll also discuss one topic, that is the dual of a dual, because that was something that I haven't discussed yet. So okay, let us start with the invariant subspaces. So invariant subspaces are basically some special type of subspaces. Okay, so let's say that T is a linear operator on V, that is T is a linear transformation from V to V, and W be any subspace. Okay, so W is any arbitrary subspace of V. So we will say that W is an invariant subspace of V with T if T of W is contained in W. That is, if you take any element of W and you apply the transformation T on it, so the result is again going to be in W. So if this property holds, then we say that okay, W is actually an invariant subspace of V with respect to T. So this is what the definition says, you can see here. So a subspace is called invariant if basically it is closed under the operator T. Okay, then we can have some examples of it. So for example, if you take the subspaces 0 and the subspace V, so you know that 0 is always a subspace of V, and V itself is a subspace of V. So for 0, if you see that T of 0 is again going to be 0, right? So it means that T of 0 is 0, which is always contained in the null space, that is 0. So that is why 0 is invariant in the T. And similarly, if you take W equals V, that is V, if we are considering that the subspace V of V, then obviously if you take any element of V and you apply the transformation T, then obviously it is always going to be in V, because T is a linear operator from V to V. So these 0 space and this W equals V are actually the improper subspaces. Okay, improper in the sense that they are trivial ones, they hold for every transformation T. Okay, fine. Now there are certain improper subspaces or certain invariant subspaces which are not so trivial. For example, if you see that the range of T and nullity of T. Okay, so range of T means, since T is a linear operator from V to V, so it means all those elements of the codomain V such that it has some element X in the domain set, right? I mean, the way we define range. So if you consider the W equals to range of T, then it is actually invariant in the T. Now to see this, actually it is quite simple, that if you take any element X in the range of T, it means what? That there exists some X in V, because T is a transformation from V to V, and T of X is again going to be in the range of T, which is equals to W. Okay, so that is why range of T is an invariant subspace. Again, if you see the nullity of T, so if you take any element from the nullity, that is X belongs to nullity of T, then what is T of X? T of X equals to 0, and 0 always belongs to nullity of T. It means if we take any element X of nullity of T, its transformation, that is T of X, is always 0, which is always contained in nullity of T. Okay, so that is why nullity of T is again invariant in the T. Example 3, this is again a very trivial example which can be seen quite easily, that if we have two linear operators S and T, so T is a linear operator and S is also a linear operator, such that ST equals to TS. Now note that not every transformations are commutative. Okay, so if you take any two arbitrary transformations, so they need not commute. Okay, because I mean, you can see from there also that two matrices are not necessarily commutative. That is, if A and B are two matrices, then A dot B need not equals to B dot A. Okay, and since every matrix is corresponds to a linear transformation, so we can also say that if you take any arbitrary linear transformation S and T, so it is not the case that it will be always ST will always be equals to T of S. But for those cases, we are considering those linear operators for which this commutative property holds, that is ST equals to TS. So in such cases, our range of S and nullity of S are also invariant under T. So this is actually an important example. Okay, and then we have the example 4. It says that if lambda is any eigenvalue, then the operator T minus lambda I commutes with T. Okay, so basically what does it say? That the eigenspace corresponding to any eigenvalue lambda is also invariant under T, and this is clear from the fact that see, T and T minus lambda I, they both are operators. So T is an operator and T minus lambda I is again operator, and they both commute with each other. That is, T and T dot T minus lambda I is actually equals to T minus lambda I dot T. Okay, so by the above result, we can say that okay, this is eigenspace will always be invariant under T, or we can also think that eigenspace is actually nothing but the nullity of T minus lambda I. So the eigenspace corresponding to the eigenvalue lambda is equals to the nullity of this operator T minus lambda I. And since we know that nullity of the operator is again invariant, okay, so from there also we can see that okay, the eigenspace is actually invariant under T, and this is what our example 4 says. Okay, so there are two ways. Either you can take S equals to T minus lambda I, and then we can say that okay, ST equals to TS, and that is why range of S and nullity of S, that is our nullity of S is nothing but the eigenspace, right? So from there also we can say, or directly we can say that since eigenspace is nothing but the nullity of T minus lambda I, and we have seen that nullity of an operator is invariant, so the eigenspace is again invariant. Okay, so now this is one more example that I considered just to show you guys how we prove actually that a subspace is invariant or not. So let's say that we have a map T from R3 to R3, okay, and the map is actually the identity map. You can see T of xyz equals to xyz. So basically it is a simple identity map. Now I considered a subspace W, and what is this W? W is nothing but set of all elements in which the first component is something, first component you will have from R, and the rest two components are 0. So easily we can see that it is a subspace. And now to show that it is actually invariant under T, what we have to do? We have to take any arbitrary element y from W, and we will see that T of y is also in W. So here that is what we have done, that we have taken any arbitrary element y belongs to W. So if y belongs to W, it implies that y is equals to some a00 for a belongs to R, that y will have this form. Okay, and what is T of y? T of y, that is T of a00 is nothing but a00, which is again in W. So we proved that actually T of y equals T of y is contained in W, and so W is invariant under T. Okay, so this is what sums up the invariant subspace. So this is just the little things that I wanted to talk about. And now there is one more concept which I didn't say earlier, because at that time I didn't say, because I thought that maybe we can take it for the last or something. So nevertheless we will see it now. So what is double dual? Okay, so dual, in our first few classes we saw what is dual space, right? Dual space was nothing but the set of all linear operators, right? Similarly double dual. So double dual is what? So double dual is actually if V is any vector space, then the double dual of V is denoted by V double star. So if you remember, so dual space was denoted by V star and double dual will be denoted by V double star. Okay, and it is nothing but the set of all linear transformations on V star. So see, dual space was the set of all linear transformations on V. So V star is set of all linear transformations on V. So similarly, what will be V double star? V double star will be set of all linear transformations on V star. Okay, and this also actually is a vector space with respect to some operation that we will see. And also it is easy to see, since the dimension of V equals dimension of V star equals n. So similarly, since dimension of V and dimension of V star, that is dimension of V and its dual, was same, so the dimension of V star and its dual, that is dimension of V double star, will also be same, that is n. Okay. Okay. So now we will just define some operations on this V double star. So for any element x which is in V and f we are taking on V star. V star means that f is some linear transformation on V. So we define LXF. Okay, so this is the notation. Okay, and this is nothing but it is defined as f of x. Okay, so first we will check that this LXF is actually linear. So LXF is, you can see that x is coming from V and f is actually coming from our V star. That is, f is a linear transformation on V. So to check whether something is linear or not, we apply the simple logic, that is, we check if alpha f plus beta g equals, so we will check Lx of alpha f plus beta g is equals to alpha time Lxf plus beta time Lxg, which is quite clear, as you can see. So all we have to do is that we have to take alpha f plus beta g time beta g of x, and now since f and g both are linear, so we can write it like alpha time f of x plus beta time g of x, and f of x is nothing but Lx of f and g of x is nothing but Lx of g. So in this way we can say that, okay, fine, our Lx that we have defined is actually linear. And also this is just a important note, we can say that if x is non-zero, then Lx is also non-zero. So the proof is actually pretty simple, that we prove it actually by contradiction. So let's say that x not equals to 0 but Lx equals to 0. So Lx equals 0 means what? Lx of f equals 0 for all f belongs to V star. What does it mean? It means that you take any linear transformation on V, Lx of f is always going to be 0. What does it imply? So that is to say that f of x is 0 for all f belonging to V star. For all f means you take any linear transformation, f of x is always going to be 0. It implies that x has to be 0, because if you consider f to be the identity map, so identity map, what does it it means that I of x equals x, right? But now since here f of x equals 0 and taking f as identity map, you will get ix equals 0, and that will imply x equals 0, which is a contradiction because we assume that x is non-zero. Okay, and this way we can see that if x is non-zero, then Lx is also non-zero. Now there is a small theorem with respect to this, which is the last theorem of this course, I would say, that if V is my finite dimensional vector space, and if we define transformation phi from V to V double star, okay, so phi is defined from V to V double star, and how it is defined? It will take some element of V, that is phi of x, and it will map to V double star, that is L of x, that we just defined earlier. Okay, so the thing is, so the theorem says that phi is going to be an isomorphism. Okay, so isomorphism means what? That phi will be linear, phi will be 1 1, and phi will be onto. So one by one we will prove all these three. So to show phi is linear, again all we have to do is that phi of alpha x plus y equals alpha time phi of x plus phi of y, which is easy as you can see. So the way we have defined phi of x, so phi of x equals L of x. So what is phi of alpha x plus y? It is nothing but L of alpha x plus y. And now since we already know that L is linear, that we just proved earlier, so since L is linear, so we can say alpha time Lx plus Ly, and again Lx I can replace by phi of x, and Ly I can replace by phi of y. So in this way we proved that phi is linear. Then I had to prove that phi is 1 or injective. So if you have to prove anything as 1 or injective, so all we need to show is that its nullity contains only the zero element, that is phi of x equals 0 if and only if x equals 0. So that is what we will prove, that the nullity has only the zero element. So we assume that phi of x equals 0, and then we will prove that x equals 0. So this is simple, that phi of x equals 0 means L of x equals 0, because phi of x equals L of x. Now, but if L of x equals 0, what does it imply? It implies that Lx of f is 0 for all f belong to V star. So this is again the same thing that we proved actually before coming to this theorem, that if x is non-zero, then phi of L of x is also non-zero. So this is just a direct implication of that, or you can also see there clearly that it implies that fx equals 0 for all f belongs to V star. And again, if you consider f to be the identity map, so we will find that x equals 0. So if x equals 0, what does it imply? That nullity of phi is only the 0 vector, and hence phi is 1. So we have proved phi is linear, we have proved phi is 1, and now it only remains to show that phi is onto or surjective. So this is again quite easy, because we can use the rank nullity theorem here. So dimension of V is what? Rank of phi plus nullity of phi. See, the map phi is from V to V double star. Okay, so applying the rank nullity theorem, we will have dimension of V is equals to rank of phi plus nullity of phi. Okay, nullity of phi we just saw that it is 0 because it contains only the 0 vector, so its dimension is 0. So what does it imply? It implies the dimension of V is actually equals to rank of phi. Rank of phi is what? The dimension of the range space. Now what is the range space here? The range space is actually V double star. So dimension of V equals n, which is equals to dimension of V double star. And also note that range of phi is actually a subspace of V double star. So what we have proved here actually is that a range of phi, which is a subspace of V double star, has dimension n, and dimension of V double star is also n. So what does it imply? That if V is a vector space of dimension n and it has a subspace of dimension n, it means that the subspace itself is V. So that is the property that we are using here. Since range of phi is a subspace of V double star and dimension of range of phi is equals n, which is the dimension of V double star, it implies that range of phi is actually equals to V double star, and it implies that phi is on 2. And now since phi is on 2, so we got phi is an isomorphism that we have to prove. Now with this, your the syllabus from the first part of the syllabus, that whatever I had to teach is finished. So I'll be taking no further classes, so there will not be any further classes for you. So this is all what I wanted to teach. Yes, I'll take one class on Sunday. Okay, so that will be just a practice class. You won't have any attendance for that. So in that class, what I'll do is that I'll try to solve all the problems that were present in the previous year question paper. Okay, so that I will do, and apart from that, I think the first part of your syllabus is actually completed. So yeah, this is what I wanted to teach. So you will have no further classes now. Thank you.